Considering a damped SDOF system subjected to free vibration. In this case, only the external force is taken as 0. We are now having a homogeneous second-order differential equation. Recalling the form of solution of x which we applied in previous video, and its partial derivatives that we used to solve for unknown velocity and acceleration responses. Let's substitute the trial solution into the equation and simplify it. Knowing the exponential term is always positive, we can safely assume the expression m lambda squared plus c lambda plus k is 0. Simplify the equation again, and now we are having a quadratic equation of lambda. Let's apply the solution for quadratic roots here. Since we could have two possible answers for lambda, the expression of x should take the following general form. From the solution for roots, we have three possible cases based on the value of discriminant. Considering the case where discriminant is 0, we can express the damping component C in terms of K and M. Let's introduce a term critical damping to represent the value of C under this situation. Damping ratio of a system, on the other hand, equals to the ratio of system damping to critical damping. When discriminant is 0, the damping ratio of the system is 1, and thus the roots for equation are real and equal. We can also transform the terms C over 2m through a series of operations. In the end, it is equal to the product of damping ratio and natural frequency of the system. Let's substitute back our findings to the equation of x, noting that the discriminant equals to 0. After simplification, we can apply initial condition to solve for the summation of unknown constants a1 and a2. In the event of discriminant is greater than 0, the damping ratio is now greater than 1, and roots for quadratic equation are now real and distinct. Let's simplify the general equation of x so that the expression consists of the exponent of damping ratio and natural frequency. Taking derivative of the expression, we get to know the expression for velocity response. After rearrangement and simplification, we obtain the definition of a1 minus a2 through the application of initial condition. Knowing the sum of a1 and a2 equals to the initial displacement of vibration, we can solve for a1 and a2 now, considering the case where discriminant is less than 0. Based on the definition of quadratic root, we should be having two imaginary roots under this consideration. In other words, the exponential terms consist of complex number. The expression can be further simplified by introducing new term, namely angular frequency of the damped system. By implementing Euler's formula, our expression is now a trigonometric function of time. From previous cases, we have solved for both a1 plus a2 and a1 minus a2 terms. Let's apply them here to obtain the final solution of x for underdamping situation. For damped system, its angular frequency is dependent of the damping ratio. Similarly, the period of system can be calculated by dividing 2 pi with that frequency. Given the expressions of displacement under three conditions, we can plot the graph of displacement versus time and inspect the behavior of the dynamic system under these situations. The movement of structure stops abruptly when it is under critical damping and overdamping cases. Thank you for watching. If you find this video helpful, please share it with your friends. We will see you guys soon. Goodbye.